Hello, my name is Jaebek Jang, and I'm going to briefly review the last class, which about constraint satisfaction problems. Generally, searching means just the process of finding what you need, and we can explain it better by the step of planning and identification. For the clearness of solving, we assume that a single agent is going to search. All actions are deterministic rather than probabilistic. All states are observable, and spaces have discrete state. Planning is sequences of actions to find the goal. At this stage, we think about path more than finding the goal. Identification problem, we concentrate the goal more than the path. And the CSPs are specialized for identification problems. Constraint satisfaction problem is a searching problem with the goal test of constraints of the values of the variables. State is defined by variable x with values from the domain D. We can use this usefully as algorithm which has a specific purpose. Now let's check about the few examples. First, map coloring. As picture shown, variable has the name which is states of Australia, and its domain is the colors. This case is red, green, blue, and constraint is that adjacent region must have different colors. Second, n queens. Each square of the board is the variables and its domain is 0, 1. 0 for the none and 1 for the queen exist. Constraint is that arrangement of queens and each queen is not attackable to others. These two examples have constraints that relate to variables. We call this binary CSP. We can easily solve the binary constraint problem by drawing the graph. Set the nodes to variable, make the arcs between the variable, which means the constraint. Let's see other examples which have constraints related between more than two variables. First, crypt arithmetic. The variable is named TWOFUR and its domain is the number 0 to 9. The constraints are that all of variables has different numbers and O plus O equal R, and you can see there has more constraints. The constraints are related to more than two variables. In this case, we can draw the graph, but it's more complicated than previous one. Another example is Sudoku. As you know, it is a puzzle of the numbers. Set the variables which pointing each square. Following domain is 1 to 9. There has a rule that any row, column, and 3 cross 3 grid with hard lined must have all different numbers. Also, it has constraints related as at least 9 variables. Lastly, the Wolf's algorithm. It is the algorithm that machine or computer interpreting line drawing to 3D object. The intersection of the sides can be considered two variables. Adjacent intersections makes the constraints. I can't clearly say what it is, but it has the clear solution of 3D interpretation. Not only these examples, in real world has much more CSPs. We can classify the CSPs for some standards. Depending on countability of domain, it divided finite domains and infinite domains. Depending on continuity of variables, it divided into the discrete variables and continuous variables. Depending on the number of related variables of constraint, it divided into unary constraint, binary constraint, higher order involve 3 or more variables. Moreover, we can select certain solution among the other solutions by considering preference. It can be set as a soft constraint. Also, we learned the backtracking search. Basically, it searches the path same way as DFS, but it finding the solution by checking the single variable at each step and check constraints while searching. Not like the DFS, it can prevent the searching goes to wrong answer which could find the goal faster than DFS. We can improve the searching with backtracking algorithm by few ideas. One is filtering. Filtering the inevitable failure early. When you assign the value to a variable, you can set the alternatives only possible for the case satisfy the constraints between the variable and assigned variables. At each moment, if the variable has the possible values to assign while satisfies the constraint with the other variable, then we can say it has arc consistency. But the arc consistency can only be applied at two variables related. So the k consistency make up the downside of arc consistency. It computes consistency from k1 nodes to the other kth node. Another idea of improving backtracking is ordering the variables or values. By choosing the variable with the most constraint, we can figure out the failure faster than without ordering. Opposite to the choosing variable, choosing the least constraining value makes the easy solution to next step. Lastly, drawing the structure of the problem can improve much. For example, graph. By doing this, problem can be divided to subproblems. Independent subproblems make solving much easier if it has. Divided problems could be computed with much less time than before. In summary, we can improve the backtracking by filtering, ordering, drawing the structure. My reviewing is over. Thanks to listen my presentation.